Page 23. So yesterday we talked about interpreting derivative graphs, which is really the major new topic that I need to go over with you. This is going to feel a little bit like review because we're just putting everything together that we've learned in terms of first derivative test for concavity. Does everyone have this this handout? So we're basically just going to go through first derivative test for concavity, and then list out all the slope and concavity behaviors, and then sketch the graph based off of that. So it is kind of like what we did yesterday, but yesterday we had to build the sign lines from the derivative graph. Now we're building the sign lines from actual first derivative and test for concavity. After we get through this, so we're going to go through page 23 and 24, just kind of putting all of this together. If we have time, I'd like for us to, well, I like to just kind of run through all the major topics from the quiz and just see if we kind of see a big picture now that you guys have had a chance to work through the quiz reviews. So I think some students were, you know, going through the quiz review. It's like, oh, you know, there's all these different things, but you know, how do we know where the steps are for mean value theorem versus EVT versus second derivative test? So I think maybe I can just spend some time kind of giving us an overview, and then if we have some time, we can do some more practice problems. But I'd like to start with this. So it says sketch the graph of the function and find the below information. If you look at the bottom of this page here, these are all the characteristics that we're going to try to fill out. So x-intercepts, y-intercepts, vertical asymptote, horizontal asymptote, domain. These, we may not have things for all of these, but these all come from the original function. So we don't need the f prime and f double prime to gather this. So this we can gather from our original function. Our first derivative test will give us information about slope related data, like interval increasing, interval decreasing, relative max, relative min. And then your test for concavity will give you information about curvature, like points of inflection, concave up and concave down. Okay. So the very beginning here, we can gather some data from the original function. We can find x and y intercepts. Well, at least look for them. So the way you find x intercepts, you're going to replace your y with 0, and then you're going to solve for x. For y-intercepts, you're going to replace your x with 0, and you're going to solve for y. So let's do x-intercept first. X-intercept, I'm going to replace the y with 0, and then try to solve for x. So if I replace y with 0, I can do some factoring. I can factor out x cubed. X cubed equal to 0, that's just going to be 0. Negative 3x squared plus 5 equal to 0. I'm going to get x is equal to plus or minus square root of 5/3. And that's just going to be some decimal value. Again, you will get to use your calculator on the quiz and the test. So just going to give you that reassurance that anything that's difficult to approximate, you can use your calculator to do. So this ends up being like 1.3-ish, plus or minus 1.3. Yeah.
Specify to do exact or exact versus approximate?
Yeah, so if the directions don't specify, then you can choose anything you want to do. But if this direction is specified, then I'll be looking for that. Yeah. So if there's doesn't specify, you can do decimals if you want. All right. So we have three x-intercepts: 0, 1.3, and negative 1.3. So I'm just going to space it out here. We're not going to need a ton of space here. So we'll do 0, 1.3, and negative 1.3. Okay, so we know that we have some anchor points already. We know our graph has to go through those points. To find y-intercept, I'm going to replace x with 0. But if I replace x with 0, my y will just be 0. And that's a duplicate. We already found that the origin is an x-intercept, so the origin is also going to be a y-intercept. So y-intercept will be the same spot, 0, 0. Are there going to be any horizontal asymptote, vertical asymptote here? No, right? It's a polynomial, so there's not going to be any breaks. There's going to be a smooth curve. So we have everything that we can gather from the original function. Now we can move on to f prime. So f prime will give us data about slope, and we can create our f prime sign line. So let's find f prime. Power roll twice. All right, so we're doing the first derivative test. What do we do after finding f prime? Yeah, set equal to 0. Yeah. So we're looking for critical points, right? Okay. So set equal to 0. I'm going to go ahead and factor out a GCF. Now I'm just going to look for my critical points. How many critical points are we going to come across? 3. Yeah. We have x equals 0, x equals 1, x equals negative 1. Okay. So this is basically the first derivative test here. Create your slope sign line.
Why did you get the negative? You did take the negative F4 before.
Yeah, so it's up to you. If you decide not to factor it out, you'll get negative x squared plus 1. You'll get the same thing. Yeah. It's just I don't have a rhyme or reason for when I factor out negative, when I don't. 0 and 1. Okay, we're choosing values to test in each subinterval against the first derivative function. And then after we get positive or negative, we know our slope behavior, whether we get a positive or negative slope. So I'm going to choose negative 2. I'll choose negative 1/2. I'll choose 1/2, and I'll choose 2. So into my first derivative function, negative times positive, negative, negative. So 3 negatives makes negative. Plug negative 1/2 in, negative, positive, positive, negative. So I have 2 negatives, so that's going to give me positive. Negative, positive, positive, negative. Again, 2 negatives. The 1/2. Yeah, 2 negatives, so still positive. Plug in 2, negative times positive times positive times positive. There's only 1 negative, so all right, so just from these arrows alone, we know what to expect. What do you expect at negative 1? Relative what? Yep. At 0, there's none, but the graph is going to flatten out for a moment because there's a slope of 0 at 0, and then it's going to continue rising. And then what do you expect at 1? Or to max. Okay, so we're going to find those order pairs in a little bit just to kind of help anchor our graph. But let's just get all the calculus out of the way. Let's get our second derivative function and do our concavity, do our test for concavity. Once everything's in front of us, we can sketch our graph. Okay, f double prime, we go back to the unfactored form, so we can easily do power roll there. So we're going to find f double prime using power roll. Yep. Good. All right, this is the test for concavity. Set equal to 0. factor out your GCF. Okay, 3 critical points. Plus or minus square root of 1/2 is around like 0.7. So here's my second derivative sine line. So I'll choose test points to use. So I'll choose -1. I'll choose -1/2. I'll choose 1/2. And I'll choose 1. Okay, into the second derivative. Positive, negative, negative. So 2 negatives makes positive. Positive second derivative means concave up. Positive, negative, negative. Wait a second. Let's see. Sorry, this is gonna be positive here. So there's only gonna be 1 negative that shows up, 1 negative that shows up. So stay negative. Positive 1/2, positive, positive, positive. Like one end, positive, positive, negative. Okay, any questions so far? I'm not so concerned about finding order pairs for the points of inflection, but I think it's good to find order pairs for relative max and min, because those are important points that kind of help shape our graph. So I'm going to find my order pairs at -1, 1. I'm also going to find the order pair at, well, we know already 0 is going to be 0, 0, right? That's going to go through that point. So let's just find the order pairs at -1 and 1. So f of -1, I'm just going to put this back into the original function. So that's -3, sorry, 3 minus 5, which is -2. And then f of 1 is just -3 plus 5, which is 2. Okay, so I think this is all we need to kind of get a good feel for the graph here. -1, -2. And then 1, +2. So we're going to do 2 versions of this graph. The first version is just dotted lines, just to kind of get the path established. And then we can go back and retrace with the appropriate curvature. So we know the graph is going to fall until I hit a relative minimum at -1. Then, sorry, and then it's going to continue rising, flatten out, rise, and then fall after that. And these points will kind of help guide our graph a little bit. We know how to go through those points there. So I don't know the curvature information, but I just know my basic path right now. Okay. Any questions so far? So we know there's points inflections at -0.7, 0, and 0.7. So just estimate where those values are. Wherever your graph lands at -0.7, highlight that point at 0, 0, and then at 0.7. So those are your anchor points for when your graph is going to experience a change in concavity. So you're just retracing the path of the graph with just more emphasis on the curvature now that you know what the curvature is. So there's concave up until that first dot there. So I'm going to just kind of over exaggerate that concave up shape. It's going to switch over to concave down. It's not going to be a full concave down, but it'll just have that portion, that concave down increasing, and then it switches back to concave up. And then the rest of the way, concave down. Okay, so now the easiest part of the problem is filling out the bottom of the page because you have all the data in front of you. You're just grabbing your max, your mins, and then your intervals of increase, decrease, interval concave up, concave down. So spend a minute, see if you can fill the bottom parts out. Don't worry about the because statements. Just know that on the quiz and test, you'll be asked to write out all the because statements. Okay, so I wrote them all out, but just to save time, you don't have to, but just know that you do want to make sure you know how to write all the because statements. So here are all the data that I gathered from my assignments. And again, this should feel easy because you have all the information in front of you. You're just pulling them from your assignments. Okay, next page, whenever you're ready.
The concave down, is it a negative root 202 or is negative? One over two.
Same thing. They're if you do negative square root of 1/2, that's fine. Yeah. I just rationalized it. It just feels more familiar to me, but it doesn't matter. You don't have to have it rationalized. All right, next page 24. So number 2, what's different about this function? There's more complexity to it, right? There's a denominator, which means that we're expecting what here? Yeah, vertical asymptotes. There's going to be some horizontal asymptotes. So But the nice thing about that is it kind of gives us some boundaries. So it kind of helps shape our graph a little bit better, having those asymptotes there. So, but we can still find all the information that we've looked for before. We can find x-intercept. Again, I can basically, you're just going to set your numerator equal to 0. If there's numerator and denominator, your numerator equal to 0 will give you x-intercept. Your denominator equal to 0 will give you your holes or your asymptotes. And then your y-intercept, you're replacing your x's with 0. So again, 0, 0 is going to show up. Let's see. Yeah, 0, 0 is going to show up again on our graph here. We do have some additional information or restrictions here. So vertical asymptote, we can set the denominator equal to 0. There's not going to be any holes because if I factored out that 9 minus x squared, I'm not going to get any common factor between numerator and denominator. So nothing cancels out between numerator and denominator. But we do have 2 vertical asymptotes at 3 and -3. We also have horizontal asymptotes, and horizontal asymptotes is essentially taking the limit as we approach infinity. And if we do limit as s approach infinity, what do we do? Compare degrees. What do you notice about degrees? They're the same. Take the ratio of the coefficients. So 2 over what? Over negative. Oh, yeah, -1. Yeah. So that means 2 over -1, which is -1. So therefore, we do have a horizontal asymptote at y equals -1. Oh, sorry, -2. Sorry, 2 over -1 is -2. So at the very beginning here, we can already establish our boundaries. We know, well, we have an order pair at 0, 0. We know our graph is going to have to work around these asymptotes here. So -3 and 3. And then y equals -2. All right, so that's all the information that we can gather, that we need to gather from our original function. The rest we're going to pull from our derivative and second derivative, our slope information, our concavity information. Okay, so let's move to f prime. Now to find f prime, we have to go through what? Quotient rule, yeah. So okay, f prime g minus f g prime all over g squared. Okay, let's do some cleanup. All right, how do we find critical points? And denominator, yeah. So even though we know the denominator are already telling us vertical asymptotes, this will still need to be on our sign lines here.
Oh, remember,
Oh, I got it. So we're going to set both the numerator and denominator equal to 0, even though the denominator we know are vertical asymptotes. They still are going to go on your sign lines, even though they have no chance of being max and mins, because they will still help separate your intervals of increase decrease. So so we're going to get 0, 3, and -3. So here's my f prime sign line. Use values to test. And you're testing them against the f prime. What's nice about the denominator when we test? It's always positive. So that's nice. You don't have to worry about the denominator. Just whatever the sign of the numerator is going to be the sign of your interval. Your denominator is always positive. So if I plug -4 in, negative over positive will be negative. Plug -1, negative over positive is still negative. Plug 1 in, positive over positive. Plug 4 in, positive over positive. All right, second derivative function. To get the second derivative, we have to go through what? Quotient and chain. What's going to come first? Quotient, yeah. The parentheses, quotient sees both the numerator and denominator, but quotient, sorry, chain only sees the denominator. So we want to apply the rule that has the larger reach first. So quotient will come first. And once we get into quotient, then chain rule will take its role when we get to that G prime, that denominator portion. Okay. So this is a little messy here, but we'll get through this one here. Okay, outsize derivative times insize derivative. Now, looking for critical points is a little messy here. Having to expand all this out is a lot of work, but there's a bit of a shortcut if we think of it this way. Imagine this as two extended terms, and if we can pull the GCF out of these two terms, then the rest will collapse a lot faster. What is shared between these two expanded terms there? If we think of this as one term and this is the second term here, they both have 36, and they both have what? 9 minus x squared. So if I can take out a 36 and 9 minus x squared from both of them, then whatever remains will be in its own parentheses, and it'll just collapse a lot faster there. So if I take out a GCF of shared factors of 36 and 9 minus x squared, so that means I'm dividing a 36 and 9 minus x squared from this piece, which will leave me with just what? Just 9 minus x squared. Okay, so I have 9 minus x squared here. And if I were to remove a 36 and 9 minus x squared from the second set of expression, I'm left with plus 4x cubed because there's x remaining, 2 remaining, and 2x. So, oh, sorry, plus 4x squared. All over 9 minus x squared squared. The nice thing here is this is already factored. We just have to put these together here. So here's my cleaned up f double prime. Okay, again, we're going to set the numerator and denominator equal to 0. If I set 9 plus 3x squared equal to 0, I'll get an imaginary number because I'll get like plus or minus negative square root, so nothing there. Numerator will give me plus or minus 3. Denominator will also give me plus or minus 3. So the only critical points I'm going to have on my second derivative sign line is plus or minus 3.
When I say cube.
Oh, sorry, it's 4, my bad. It's this squared, which is 4. Oh, my bad. It's my denominator squared. Okay, I'll test -4. I'll test 0. I'll test 4. This is always positive. I can ignore that. So this will be negative. This is always positive. I can ignore that as well. So whatever this gives me is going to be my sign. So I have negative over positive, which is negative. Plug 0 in, I get a positive over a positive. Plug 4 in, I get a negative over a positive. You can also put this into your calculator to kind of give you an idea how the graph is going to be shaped. But we know that initially our graph is going to be decreasing, but experiencing concave down. So the only way that's going to fit along with hugging along the asymptotes will have to be something like this. Our graph is going to be experiencing a relative minimum at 0, but then meanwhile experiencing concave up. So it has to be something like this. And then to the right, we're experiencing increasing slope, but concave down. So the only way increasing concave down is going to be shaped along the asymptotes. We'll have to look like that.
Equitable sign line.
Yeah.
Why did you only use -3 if they're multiple?
So this 9 minus 6 squared gave me plus or minus 3, and so did this one. So there's duplicates here. And then 9 plus 3x squared, I'll get 3x squared equals -9, and I'll get x squared equals plus or minus root -3. And so imaginary numbers, we can ignore it. It's not a solution. Yeah, just ignore imaginary numbers. We only deal with real numbers in this course, so there's no solution there. Okay, let's fill out all of our interval increase, decrease. And then the domain is just working around the asymptotes. So no max, no point of inflection. We do have a relative minimum. And then all your intervals you can just pull from your sign lines. Okay, we have a little under 20 minutes remaining. I think maybe a helpful activity would be for me to kind of go through all the major steps of all the content that you're going to have to do for your quiz. And that way I can kind of highlight the big picture of everything that you're going to have to do for your quiz. Again, we're going to do a full another full quiz review on Monday after the break, but I think maybe it's good to kind of put everything together as well. So if you can get out a sheet of paper, and I'm just going to run through all the major topics and talk about the steps surrounding them to help you kind of review, but then also help you see the big picture.
I'm gonna say what you're saying, so what's the one?
Are you allowed to do the game?
Yeah.
All right, so quiz review topics and steps. The first is if a problem says find a critical point, all you're going to do is you're going to find f prime. And you're just going to set the numerator and denominator of f prime equal to 0. But sometimes you may need to find common denominator. So that you can get it down to one fraction. And then you can set your numerator and denominator equal to 0. And find your critical points. Okay. There's no restriction here. Whatever you find will be your answer. There's no need to worry about some boundary that's involved with EBT. Critical points is just find the derivative, and if you have a mixed fraction, merge them together into the same fraction, set the numerator and denominator equal to 0, and then you're done. Okay. Second major topic is extreme value theorem. Or EVT. The purpose of EVT is you're trying to find your absolute max and your absolute min. Over the interval of the graph, you're just trying to find what is the highest y value and what's the lowest y value, and that's our goal. We do have one condition, and that is required for you to state in order to move on, and that is your function continuous on the closed interval from A to B. If there is no denominator, then there's nothing to worry about. If there is a denominator, then you want to make sure that if there's a whole or asymptote, that the whole or asymptote is not interfering with the interval. If the whole or asymptote is interfering with the interval, then you stop the problem because the function is not continuous. But if the whole or asymptote is outside the interval, then we can say the function is continuous, no issues there, and we continue with our reservoir theorem. Your next step is you're going to find critical points. Now, at this stage, you already have two candidates, right? What are the two candidates that you're always going to be testing no matter what? Endpoints, right? You just may or may not have additional test points depending on if you find critical points. So critical points, same steps as above. You're just finding f prime. If there's a denominator, then you're going to set numerator and denominator equal to 0. But our critical points need to be living where? Inside the interval. Yeah. If you don't have any critical points inside the interval, then there's no critical points to test. If some critical points are inside and some are outside, you only care about the ones that's inside. And then once you have established any potential critical points, then you're just going to test endpoints and critical points into your f of x function. Right? Because now you're looking for location. And then your absolute max is your, and then just provide your absolute max y value and your absolute min y value. And that's all I care about. I just care about the y values.
Just plugging back in.
Yep, just into the original function. Now make sure that you don't plug it into f prime, that you're putting your critical points and endpoints once you've established valid critical points into the original function. And then you're just identifying your highest and lowest y value, and that's all we care about. Yes. Right, or slope is 0 or slope is undefined. So let's say the graph looked like this. We want to consider places where slope is 0, and that's why we set the numerator of f prime equal to 0. But there's a denominator of f prime. We also want to consider that because it could be a sharp turn, and that sharp turn we don't want to forget about. Yeah. Good. Any other questions with EBT? All right, the next major topic is mean value theorem. And the whole purpose of mean value theorem is you're trying to find a place on the curve where the slope matches your average rate of change. So you're always going to be given enough data to get your average rate of change. You're just taking your endpoints, plugging them into the original function, getting your order pairs, build your slope, and your average rate of change is the first thing you want to do. You want to establish, okay, what am I trying to guarantee here? Am I trying to guarantee a slope of 0? Am I trying to guarantee a slope of 4? Am I trying to guarantee a slope of -5? Okay, whatever slope that I build, I'm then looking for it on my derivative function. So we do have two conditions that we have to establish. The first is that our function needs to be what? Yeah, continuous and differentiable. So continuous is with brackets. And then differentiable is with parentheses. Again, you only have to worry about testing the first condition. That means if there's an asymptote and that asymptote is not interfering, then you can just go ahead and this will follow along with it. So just worry about getting that first condition passed. The second one, at least the one that I give you, it'll pass both conditions if you can pass the first one. Yeah. Right, I won't give you any ones that have sharp turns. We'll talk about ones that do later on, but that's unlikely to happen on the AP exam. If they're asking you to do mean value theorem, typically they are wanting you to go through that full process, but we'll talk about those exceptions later on. Okay, once you get past your first two conditions, then you're going to begin building your formula. So your first goal is trying to get that average rate of change to show. That means you're trying to get that slope between the two endpoints. It could be a slope of 5, it could be -4, it could be 0, it could be 3. Whatever slope you find, that is what you're trying to look for on the curve. Once you find that average rate of change, then you're building your derivative function, and then you'll set them equal to each other. And then you're asking the derivative to look for a place on the graph where this slope is occurring, whatever that slope is. And then once you find your c-value needs to be inside the interval from A to B. You're guaranteed at least one c-value or one solution for x value. but it's got to live between the two endpoints. So if it lands at the endpoint, it's not close enough. It needs to be between. So this is the most, at least on the quiz, I think this will be the most labor intensive because you have to spend the time to find your order pair at the endpoints, and you have to find the slope between the two endpoints, and then you got to find the derivative function, and then you got to set them equal to each other, and you got to solve for x. But everything is within this formula here. All right. Any questions with mean value theorem? Okay, next up, Rolle's theorem. Which is identical to mean value theorem, same condition, continuous differentiable, same process, find the slope, set equal to the derivative, but there's one exception here. This piece has to be what? Slope has to be 0. And that's the only thing that Rolle's theorem is specific about. Mean value theorem, this can be slope 0. This can be any number that you find. But Rolle's theorem, the slope has to be 0. Otherwise, we can't move forward. So I will just say same as mean value theorem. But your average rate of change has to equal to 0 in order for you to move forward. That's the only restriction for Rolle's theorem. But other than that, it's the exact same process as mean value theorem. Okay. Let me go to the back. I think these next few should be more familiar because we've been doing them a lot more often, and that's the first order test for concavity. So next up, first derivative test. So the purpose of first order test is you're just trying to find your behavior in terms of the slope. So you're trying to find your intervals of increase, decrease, relative max, and relative min. You're just trying to find where is my graph rising and falling. So you're just going to set f prime equal to 0. And then you find your critical points. And then you're just going to test your critical points. And we've been doing that a lot, so this should feel familiar to you. And then on the quiz, you're going to be asked to find these locations, but then also justify with because statements. All right, next up, there's the test for concavity. And this is where you're going to get all your data from your second derivative function, but now your sign line is now going to tell you something a little different, even though the process will feel the same. It will be intervals of concave up, down, POIs. So you're going to set f double prime equal to 0, find your critical points, and then test your interval and see if there's any change in signs and your intervals of concave up and concave down. Again, same thing. You're going to justify with because statements. All right, next up, this is called the second derivative test. And this does the same thing as the first derivative test. This helps us find relative max, and relative min. But it goes down a different path than first derivative test, even though you get the same data to test, but you're going down a different path. You're not going to create a sign line. So here's the steps. First thing is you're going to set f prime equal to 0, find critical points. Okay, but no sign line. We're not going to do a sign line for this process. Second step, you're going to plug your critical points that you found into the what? Yep, into the second derivative function. And then you're going to use the concavity data to determine if you have a relative max, relative min. So here's an example here. Let's say you set f prime equal to 0, and you found your critical points to be x equals 4 and x equals 8. Right? You know these are the candidates, or you're testing these candidates here. Okay, you find f double prime, and you're plugging these values in, and you're looking at the data here. So second derivative of 4, let's say it gives you 25. That number is not important. It's the fact that it's what? Positive. Therefore, what can we conclude? Yep, this is concave up, which looks like this. You know that the point that you're looking at must be a relative min, so you can conclude that there's a relative minimum at x equals 4. Don't involve the 25 at all. The 25 is not a location. It's an abstract number. If you want to find the order pair, you have to plug it back into the original function. But at the very least, we know there's a relative minimum at x equals 4. Let's say f double prime of 8 is equal to negative 29. What does that tell us? Yeah, it's concave down. All right, no homework. Hope you guys have a great fall break. We will do a full review Monday. Quiz will be Wednesday after break.
I have a question. I think I'm weird, but
Yeah, I'm surprised.
That's great.
I don't know why you're out, but I hope everything's good.
Thank you. Appreciate it. Thank you.
No.
I hope all the best.
Thank you.
Whatever.
Appreciate it.
thank you.
Thanks, guys. Have a great break. Bye.
It was low about Canada.
Nobody thought you were gonna get this far. Nobody thought you guys could do what you actually did. Former players, parents, the school, everybody down.
Thank you.
Thank you. Have a great day. You too.